Hi, I'm Kristin Linn. I'm an assistant professor of biostatistics at the University of Pennsylvania, and I'm going to introduce causal inference using the potential outcomes framework. We'll start by considering the scenario where we are running a randomized trial or an observational study with a point exposure denoted by random variable A. So A will be a binary variable that takes values 1 or 0 and indicates whether an individual receives a treatment or an intervention or an exposure versus a control. We'll denote our outcome by Y. So Y will be a random variable that can be either continuous or discrete, and we're going to be working with scalar values or univariate outcomes Y. Our objective is going to be causal inference on the effect of treatment or exposure. So here are a few examples. We might be interested in estimating the effect of ocrelizumab on the total volume of new white matter lesions compared to another treatment like beta interferon. Or we might be interested in estimating the effect of prenatal drug exposure on cortical gray matter volume. In the first example, this would likely be tested using a randomized trial, although we might be doing some sort of secondary analysis using data that is collected in an EHR. The second example, we wouldn't be able to randomize because it would be unethical to randomize pregnant women to take drugs or not. The premise of the potential outcomes framework is that we assume that every individual has a set of potential outcomes, and these characterize the response to each level of the exposure had the individual been assigned to it, possibly contrary to fact. So we assume that, or we'll denote the potential outcome if an individual is exposed by yi of 1, and then we'll similarly denote the potential outcome if an individual I is not exposed by yi of 0. Then using this notation, the individual level causal effect is the difference between these two potential outcomes for individual I. So as an example, suppose I wanted to know if eating salmon every day would prevent me from getting Alzheimer's disease. If I could observe myself in a world where I eat salmon every day, as well as in a world that's exactly the same with respect to every single factor and timeline and so forth, not eating salmon every day, then I could observe the causal effect of eating salmon. So here are some scenarios if I could observe both of these potential outcomes of me eating salmon and not, as well as the difference between the two, so the causal effect. In the first two situations, rows 1 and 2, eating salmon has no effect. So in the first row, I unfortunately get Alzheimer's disease no matter what. And in the second scenario, I don't get the disease, whether or not I eat salmon. So there's no individual level causal effect for me in those scenarios. In row 3, if I eat salmon, I don't get the disease, and if I don't eat it, then I do. So here, salmon has an advantageous causal effect where it prevents me from getting the disease. And then finally, there could be a scenario where eating salmon is actually harmful, and so in this case, if I do eat it, then I get the disease, and if not, I don't. The fundamental problem of causal inference is that for any individual, we generally can only observe one of the two potential outcomes, and therefore we can't observe the individual level causal effect. So for example, if I decide to eat salmon every day, I can only observe yi of 1. Although individual level causal effects are generally unknown, we can often estimate population level causal effects. And so our parameter of interest in the following discussion is going to be the expected value of the difference between the two random variables that are the potential outcomes. So you can think of this as the average over all the individual level causal effects. And I want to mention that throughout this talk, we're going to assume what is sometimes called the consistency assumption. So here we assume that the observed outcome is the potential outcome that corresponds to the observed level of exposure. So if I actually received treatment AI or A sub I equals 1, if I receive treatment A equals 1, then I get to observe my potential outcome Y of 1. And vice versa, if I receive A equals 0, then I get to observe YI of 0. Consistency doesn't always hold. So when consistency does not hold, it means that one individual's exposure affects the potential outcomes of another individual. And a good example of this is a vaccine study where if individuals in my household or in my network get vaccinated, that's going to affect my potential outcomes. I want to quickly review some statistical concepts that we're going to use throughout this talk. So first is that the unconditional or marginal expectation you can think of as the average or the expected value across all possible values that a random variable can take in a population. Two random variables u and z are independent if the probabilities with which u takes on its values are the same regardless of the value that z takes. So we'll denote this as, we'll say u is independent of z and denote this using this symbol that looks like an upside down T. We'll write the conditional expectation in this way, and this reads the conditional expectation of u given z equals little z. And this is the average across all values of the random variable u for which z takes on the set value little z. If u and z are independent, then the conditional expectation is equal to the marginal expectation. So the conditional expectation of u given z is equal to the marginal expectation of u. This is a really convenient statistical identity that we'll be using. So the marginal expectation of u can be written as the expectation of the expected value of u given z, where the outer expectation is with respect to the distribution of random variable z. And then finally, we have this fact that the expectation of a function of two random variables, if we condition on one of them, then we can remove or pull out the function of the variable that we're conditioning on. So in this case, we have the expected value of some function f of z times u conditional on z. We can pull out f of z, and so that expectation on the left-hand side is just equal to that function of z times the expected value of u given z. So now let's go back to talking about the average causal effect. So we're interested in this causal parameter, the expected value of the difference between the two potential outcomes. And we're going to let this notation, the expected value of y of little a, denote the expected value of y if everyone receives treatment A equals little a. So this is still a potential outcome. We're just using more general notation. So then taking our average causal effect of interest, this expected value of the difference, the expectation operator is linear, and so we can distribute that expectation and write our average causal effect as the expected value of y of 1 minus the expected value of y of 0, and now we can focus on identifying and estimating these two quantities. So if we go back to thinking about parallel worlds or parallel universes, if we had two worlds that were exactly the same, one in which we assign everyone to be exposed, so A equals 1, one in which everyone gets the control or is unexposed, A equals 0, if we could observe all the outcomes from these two worlds, then we could simply take the mean of each one, and the difference would be our average causal effect. Of course, we can't in general observe those two worlds. This is the fundamental problem of causal inference. And so our average causal effect of interest is not necessarily equal to the difference of the conditional expectations of the observed outcomes given those who get treated and not. So the expression on the right-hand side is with respect to our observed data, our observed outcomes. And these conditional expectations restrict to the subpopulation who actually received the treatment or were exposed, or vice versa for A equals 0 who were unexposed. And the problem is that these subpopulations that are exposed or not exposed may differ in important ways that affect the outcomes. So for example, in our prenatal drug exposure example, pregnant women who use drugs may be less likely to have access to healthcare and may be more likely to experience food insecurity. And so any effect that we estimate using the observed data may not be due to drug use, but may be confounded by these other factors. So going back to our parallel worlds example, in reality, we only get to observe a portion of these parallel worlds restricted to the subpopulations that are actually treated and not. And so the average difference of the outcomes that we observe from these two different worlds defined by the treatment assignment is not necessarily equal to the average causal effect. And that leads us to formalizing this with the definition of a confounder. So a confounder is a characteristic that is associated with the likelihood of being exposed and associated with the potential outcomes. So we have this diagram here where we have the effect of the exposure A on the outcome Y, and it's confounded by this variable or set of variables X that both affect A and Y. So now to estimate the average causal effect, we have to appropriately account for confounding. And any method that we choose to use is going to require certain assumptions that, if they are wrong, may lead to bias and incorrect inference. The reason why randomized controlled studies are the gold standard for causal inference is that randomization eliminates the association between the confounders X and the exposure A. So we no longer have this arrow from X to A, and we therefore don't have any confounding of the A-Y relationship. And so in this case, we do have that our average causal effect is equal to the difference in the conditional expectations that are restricted to the subpopulations defined by the given treatment. And I'm just going to walk through and show why this is the case. I'm sure that this will be a review for some of you, but just setting the foundation here. So the expected value of the potential outcome y of little a is equal to the expected value of y of little a conditional on a, in this case where we have randomization, because our treatment A is independent of the set of potential outcomes. So our marginal expectation is equal to the conditional expectation when these things are independent. Now we use the consistency assumption to substitute the observed outcome y for the potential outcome. And then finally, bullet points 1 and 2 here imply that our average causal effect is equal to this expression that is written with respect to the observed data that we can estimate using the data that we have from our study. So that was a randomized study. So what if randomization is not possible, either due to ethical reasons or infeasibility? So for example, we can't randomize people, the pregnant women, to take drugs or not. That would be unethical. We wouldn't be able to randomize different countries to implement different versions of, say, a healthcare policy. So in this case, in an observational setting, we need to adjust or control for all confounders. So if all confounders of the A-Y relationship are measured and contained in X, then among individuals who are observed with the same values of the confounders X, there will be no association between the exposure A and the potential outcomes. So we have this independence between our set of potential outcomes and our treatment mechanism A conditional on X. And our assumption, so we assume that there are no unmeasured confounders, which is almost never verifiable. I will mention that it's likely not true in a lot of cases, and so there are methods to, such as sensitivity analyses, that check the robustness of the results of a causal inference study to unmeasured confounders. But if we do assume that we don't have any unmeasured confounders and we are properly adjusting for the confounders that we have measured, then we can obtain unbiased estimates of the average causal effect with appropriate adjustment for confounding. And I'll show here, I'll just walk through the derivation from the potential outcomes to the expression using our observed data. So here we start off with the difference in the expected value, the marginal expected values of the two potential outcomes. That's our average causal effect of interest. And we first use the iterated expectation fact that is very convenient, where we write these marginal expectations as a double expectation, with the outer expectation being with respect to the confounders X, and the inner expectation conditioning on X. Once we condition on X, we have the independence of the potential outcomes and the treatment mechanism using our assumption of no unmeasured confounders. And so this second equality line here is now conditioning on A after we've conditioned on X, because A is independent of the potential outcomes. And then once we condition on the observed values of A, we use our consistency assumption to substitute the observed outcome Y for our potential outcomes. And now we have this expression. We've identified this average causal effect in terms of our observed data. So the above derivation suggests our first strategy that we'll talk about for adjusting for confounders, which is using regression modeling. And so this suggests that to estimate the average causal effect, we might posit a model for the outcome regression, the expected value of Y given A and X, and then average the model-based estimates of the difference of these conditional expectations over all the observed values of the confounders X. Estimation of the average causal effect via the previously outlined regression procedure requires that the postulated model for the conditional expectation of our outcome Y given A and X is correct. So this is a critical aspect of estimation of average causal effects. We need the model for the outcome given treatment and confounder to be correct. In other words, the outcome regression model must be identical to the true regression function, the true expected value. If it is misspecified, if we do not know the form of this conditional expectation, then the average of the difference in the conditional expectations that we would use to estimate the average causal effect may not be a good estimate of our target parameter. The second adjustment strategy that we'll walk through is using weighting. And for this, we're going to introduce the propensity score, which is the probability of exposure given covariates or confounders X. So we'll denote the propensity score by E of X. And this is, again, going to be the probability of exposure, so the probability that A equals 1 given a certain set of confounders. And again, under the no unmeasured confounders assumption, if we include all of our confounders in this propensity score, then the potential outcomes are independent of the exposure or of the treatment mechanism given the propensity score. So before we were conditioning on the full vector of covariates, but actually we can just condition, if it's correctly specified and includes all of our confounders, we can just condition on the propensity score and we get this independence of treatment and potential outcomes. So now one way to estimate the propensity score E of X is to posit and fit a logistic regression model, assuming that we have a binary exposure variable. Although recently there's been a lot of work using more flexible machine learning models to estimate propensity scores. And so in fact, any model that returns a valid estimated probability of the exposure may be employed for modeling the propensity score. And so I'm not going to go through the full derivations of these expressions, but under no unmeasured confounders, we have expressions for the marginal expected values of the potential outcomes that turn out to be functions of the observed data and the propensity score. And in fact, this motivates estimates of the average causal effect that are based on outcomes that are weighted by the inverse of the probability of the observed exposure of each individual in the study. And these types of estimators are often called inverse probability weighted estimators. So to give a little bit of intuition about why this weighting works, I just want to show a very simple toy example here where we have a sample. And in this sample, we have some imbalance, or we have a confounder, which is age, where the individuals who are exposed with A equals 1 tend to be older, and then those who are unexposed or don't get the treatment tend to be younger. In this case, we can model and estimate the propensity score. In this case, it's we can just kind of look at the data and see what it is, but because it's a very simple example. But for example, the probability that A equals 1, given that an individual is old, is 3/4. The probability that A equals 1, given that an individual is young, is 1/4 in this sample. And the weight that we're going to use is 1 over these probabilities. So this is the inverse weighting part. So someone, for example, the exposed, a young person here who's underrepresented in this data set is going to be upweighted. And what these weights end up doing is creating a balanced conceptual sample where we can estimate our average causal effect within this balanced conceptual sample that is no longer confounded by age, because we have balance across the treatment groups with respect to age. There are other adjustment strategies for dealing with confounding. For example, we can do regression adjustment using the propensity score as a covariate instead of individual confounders. Of course, we still have to correctly specify our models. We could stratify by confounders or by the propensity score and estimate the average causal effect within strata. There are certain rules that are used to combine estimates from each strata in order to get the overall average causal effect. Many of you are probably familiar with matching or matching estimators, and so with these we would create matched pairs or groups based on the propensity score or maybe another distance metric of choice, and we would estimate the average causal effect using only the data that we retain from our matching procedure. There are double robust estimators that require us to model both the outcome and the propensity score, but the nice thing about these types of estimators is that we only need to correctly specify one of those two models. As long as only one of them is correctly specified, then we're able to make correct causal inference, and there are some statistical advantages to these estimators as well in terms of efficiency. So for example, in a randomized trial, when you know the propensity score, you know the exact probabilities of being exposed or not, or getting the treatment or not, these double robust estimators can oftentimes be more efficient than other standard regression-based estimators. I wanted to briefly mention some other causal parameters of interest. We've mainly focused on the average causal effect, but sometimes you might be interested in estimating the average treatment effect on the treated. So that subpopulation that is defined by those who tend to get treatment, you can estimate an average causal effect for that population. We might be interested in estimating the average treatment effect amongst individuals that have a particular value of the covariates. And this is really interesting in terms of this idea of precision medicine and heterogeneity of treatment effect, where certain drugs might work better for certain types of individuals. And if we can figure this out, if we can estimate these treatment effects for different subgroups of people, then we can better personalize treatment by tailoring drugs to individuals that are optimal for them. Mediation analysis is also oftentimes of interest in causal inference, and particularly I think is of interest oftentimes in imaging studies. So with mediation, we can decompose the total effect of an exposure into a direct effect of that exposure on the outcome, as well as indirect effects that are due to one or more mediators. And then I want to briefly mention some, or wrap this up by mentioning some challenges with respect to causal inference in biomedical imaging. The first of which is the high dimension and just complexity of the data. So if we're trying to do causal inference and our outcome is an image, it would be probably very difficult, if not impossible, to correctly specify a model for an exposure on a high dimensional image. Also, we might have some very complex confounding going on that might be difficult to specify models for that as well. There are also many issues when trying to think about causality in the context of predictive modeling. For example, with multivariate pattern analysis, we might use some sort of machine learning model to learn an image biomarker that might aid diagnosis or prediction of a disease progressing. But these types of models might suffer from poor generalizability if we train them on an unrepresentative sample. And this is highly related to the idea of confounding, because if we take our trained model and try to apply it to a population where maybe the distribution of certain factors like age and sex and so forth are different than what we trained the model on, we can end up with poor performance of our image-based biomarker. And then I'm really looking forward to my colleagues' talks for the rest of this tutorial, and so they're going to mention many more case studies and challenges, and I'm very much looking forward to the rest of this tutorial, and I hope you are too. Thanks for your attention.